This is Joel. We'll continue with our discussion on ACI. Till now we have talked about a bunch of things, why we need ACI, the logical model, the physical model, how are they connected and all of that, right? So in this video we'll dig deeper into ACI, especially around the packet forwarding, the endpoint learning, and all the cool stuff, right? How the bridge domains work, how the L2 works, L3 works, and so on. Cool. So that being said, let's see what happens the first time the ACI comes up, right? So you have your amazing spines here. Let's put in some leaves, right? And we have talked about the downstream part till now, haven't we? We talked about, and let me also, before I forget, put the epic. Let's say I've connected epic to only one single guy, right? And this one generally is connected this way, right? And this is connected to everyone else. All right. So we have talked about what? We have talked about till now. We have talked about how the endpoints, when they come and connect, right? What are the configurations, right? And we have talked about the physical and logical model using which, they get the endpoints when they connect up to the interfaces, right? How they become part of the fabric, or how they connect up to the fabric, right? So that's something which we have talked about till now, right? And so stuff which we have touched upon are our VLAN pools, our domains, our AEPs. We have talked about the IPGs, and on the logical side, we have talked about how when an endpoint comes and connect to the ACI, it gets put in a particular EPG, right? Based on the VLAN which it is carrying, based on the port it is coming on, right? It gets put in a particular EPG, and then that EPG rolls up to a bridge domain, the bridge domain rolls up to a VRF, and that again in turn rolls up to a tenant, right? So that's all stuff which we have talked about. But when you first turn on, there are a bunch of things which are very important, right? First thing is when you bring this epic on, right, the first time, it's going to ask you for some basic things. Like, for example, things which I can remember, it's going to ask you for a IP pool, right? So it's going to ask you for an IP pool, and I think by default, I think it will show you that probably this one is the default 110 network /16, if I'm not wrong, right? So this is the IP pool which your ACI will use to what? To kind of for the IP addresses for each of the devices which are part of your ACI fabric, right? So it's gonna pick, if you take this as the IP pool, it's gonna take this guy and it's gonna give 10.0.0.1. This one probably is gonna be .2, .3, .4, right? 5 and 6, right? So something like this. So it's gonna pick this pool, whichever pool you have given, and it's gonna use that to name or to identify each of the devices. It's gonna use that IP address for each of the devices in ACI, right? Cisco also kind of recommends, to keep this subnet unique, right? I mean, technically, it should not interfere, even though your clients also can use the subnet, because this subnet generally resides where? So this IP pool, what you do, they basically reside in what we call as that infra tenant, right? I talked about tenants in the previous video, so you can go and check. There are different kinds of tenants. The infra tenant is basically the tenant which takes care of the whole, the fabric communication, right? Basically over here. So there's an infra tenant, inbuilt kind of a tenant, which is responsible for the whole communication which happens between the leaves and spines. So this pool is kind of inside that. So technically, it should not hamper your plans if you have some other, IP pool, which is, I mean, if you have a bunch of endpoints using the same IP pool, technically it should not cause an issue, but Cisco still recommends you to keep it unique, because that way, in case if you have some kind of inter-VRF routing and all happening in future, it shouldn't cause an issue, right? So that is one thing. Then, so yeah, and the other important thing is, before I forget, ACI uses what we call as IP unnumbered, right? So it uses IP unnumbered to kind of configure the IP addresses on these nodes, which means every of this interface which is here is going to have the same IP address, right? Which is in this case .5, and here it's going to be .6. ACI doesn't use a separate IP address for every interface, right? And that's the cool thing about IP numbered, right? IP numbered generally allows you to process IP packets without configuring a unique IP address on an interface, right? And the whole idea, it basically works by kind of borrowing, an IP address from another interface. Basically, it's been there for a long time. It's not a ACI innovation as such. It's been there since a long time. People used to do this on serial interfaces mainly to save up on IP addresses, right? Like back in the day when you had that classful addressing, right? Even between two routers, right? I mean, the smallest I could go was /24, right? So as a result of that, I had to use such a big subnet, even though I'm connecting directly connected where I want just two IP addresses, but I still had to use a /24 subnet, right? During the days of the classful addressing. So that time people came up with this IP numbered where they said, look, I mean, let's try to, like, for example, if you have something like this, right? You have an IP address here, you have an IP address here. These two interfaces can kind of like borrow the IP address from here, and that way you don't have to configure any IP address over there, right? You can look up more on IP number if you want, but that's something which ACI uses as well to kind of save upon the IP address space. The other thing is ISIS, right? I've talked about this before a little bit, but just to affirm that ISIS is basically the routing protocol which is used here, right? I've told you that this is L3, right? And VXLAN is basically helping you to connect the L2 domains via L3. So the L3 here is generally built by the ISIS, and ISIS is used because of its scalability, nothing else, right? So ISIS mainly uses that LSP packets, right? Link state packets. For extending your routing information. This LSPs generally contain what we call as, this has LSPs, and that in turn has your TLBs, right? So each of which kind of like, represents a piece of routing information. And unlike take for example, OSPF, where you need to have multiple ASAs, right? One for each type. And as a consequence, it's more chattier, I would say, right? When compared to ISIS. So that's why ISIS is kind of preferred and it's more scalable when you talk about like flat networks, right? So that's important, but nothing very fancy here. Your traditional ISIS config is done between the leaves so that there is L3 connectivity between all these IP addresses which we have used. The other one is we also need a VLAN, right? Again, these are all the stuff which, so like for example, this one, right? The IP pool, the VLAN, all of this you have to configure the first time you bring the APIC up, right? So there is a VLAN as well. I think I think it was using something like 3967 back in the day. I'm not sure if this is still the VLAN number which is used. There is no much significance for using this VLAN number. It is generally chosen because no one would go and configure VLAN something 3967, right? So assuming that they use this VLAN is generally like I said, it's basically called infra VLAN. Right, the APIC which is there over here, it communicates to the ACI via this VLAN, right? This VLAN is obviously associated with this infra tenant which I was talking about, right? And the main use case of this VLAN is for the internal communication between the fabric nodes, right? And also the APIC, that's it. So this is really needed, and you have to make sure that you use the correct one and you don't use this VLAN anywhere else, right? Because then you would basically end up mixing all the traffic and kind of black holing stuff. So so these are a bunch of things which you need to be 100% sure, like plan your stuff well before you deploy your ACI, because this is something, once you decide on something, once you configure, you can't like easily change. I think literally you can't change, I believe. So just a heads up that you need to keep in mind. Okay, sweet. All right, so next, so we've talked about a bunch of protocols here, right? Let me just recollect. So we've talked about ISIS, we talked, okay, I think we talked just about ISIS. All right, so the other important thing is, let's talk a little bit about VXLAN, right? So let me just get rid of this guy, because that's important as well to understand the whole picture, right? Now, you'll probably find a detailed lecture on VXLAN on my channel if you want to learn more on VXLAN, EVPN, BGP EVPN and all of that. The VXLAN which is used in, at least in the fabric, right, mainly is what we call as the iVXLAN, right? It's a very interesting version of VXLAN. That being said, let's talk a little bit about this. So, for example, right, so we've got, I don't know, maybe two switches. you've got your servers connected here, right? So we've got maybe this is your data center, right? This is your data center which you recently sprung up, and you just have 2 switches probably, and a customer has kind of bought your services, right? So a customer wants to host their servers in your data center. So say, let's call the customer, I don't know, A, right? So they have 2 servers and we have connected them to 2 of our switches, maybe in a VLAN, I don't know, maybe 10, right? And this one, this is your switch 1, this is your switch 2, right? All right, so let's also put in probably the VLAN 10, because it's a trunk link. This is going to be a trunk link, so you're going to have VLAN 10, right? So, but then imagine someone else also wants to host their services, right? So let's put in another color. Maybe over here there is another server coming in now. Maybe we got a new customer, right? And we want to put that guy in VLAN 11, which is fine, and this is going to be B, right? But and obviously we will need to have some SVIs over here, right? We'll have to have SVIs which is 11, and we'll also have to have the SVI for 10 as well on both the guys, right? Because that's how you will basically be able to enable routing, right? In case, I don't know, maybe 10 wants to talk to 11, right? Or maybe 10 wants to go out to the internet, because this will generally connect up to some kind of a router or out to the internet, right? So if you want some kind of routing, then you would really need to enable SVIs, right? Now, just while we are here at layer 3, right, you can use VRF to kind of do what you call as multi-tenancy, right? Which is basically like, for example, I could have a VRF separately for customer A and another one for B, right? That way my customer A can use an IP address 10.1.1.1, and even my customer B can use the same address as well, right? So because as your data center becomes big and big, you would probably run out of IP addresses, right? So you would want to create VRFs and also to keep your traffic completely isolated from your other customer, right? You don't want at some point, the customer A and B's traffic to get to be able to talk to each other, or it might end up creating all privacy issues. So technically, if you want to have supply routing tables for each of your customers, then you go for VRFs. Now that's at layer 3, right? This is happening at layer 3. But similarly, what is the counterpart at layer 2, right? At counterpart for layer 2 is just VLANs. At least in your traditional networks, it's just VLANs. So it becomes really tricky when the number of customers increases, right? Because you just have a hard limit of 4094 VLANs, and remember, this whole thing is one single broadcast domain, so you can have just a maximum of 4094 VLANs down here, right? So which means which kind of means you can have 4094 customers in your whole data center. Now, when people build data centers, they build huge ones, not obviously just 2 switches. They're going to build huge server farms and huge data centers, right? And they really can't get the ROI for their business if they're going to have just 4,000 customers, right? So that's where VXLAN comes into play, right? So in VXLAN, what you do is you kind of take the existing infra, what you have, right? Something like this. So you take your existing whatever you have, the 2 switches, and you put a L3 link over here, right? As soon as you put an L3 link, what did you do? You basically ended up isolating this guy and this guy, right? The L2 domains of these both are isolated, right? So now you can still have your customers, I don't know, 10 and 11, the earlier ones, right, here as well, right? But because of the L3 link, they are kind of like completely, closed from the outside world. The L3 link literally breaks the big L2 domain, right? But what this also brings to the table is now each of the switch supports 4094 VLANs. Here also you have 4094, and these 4094 are unique from the ones on the other side. They are completely unique. They are different. They are different broadcast domains, right? Now technically, no one would go for 4094 or whatever, right? That's a huge number. You don't have any switches, I think, which will support so much because before hitting like the platform hardware limit. But you get my point, right? You have flexibility of a huge number, maybe not 4,000, but at least a big number, right? And this is where your VXLAN comes into play. So VXLAN, what it does is, it basically does this job of connecting the broadcast domains. Like for example here, it can connect, sorry, not this, or you can, but just to keep it simple, VXLAN is the guy who you bring to the, bring to a table when you want to connect, two broadcast domains here, right? In simple terms, what it does is, it basically, you still, the packet which is coming here, you still have the inner packet, right? But the outside, you basically encapsulate it with the VXLAN, header, and then you have like a UDP header. So generally, a VXLAN packet is generally what they call as actual payload inside a UDP, right? Inside an IP, right? Because you're going to have an outside IP header as well, and obviously corresponding outside L2, but this is generally going to be for next stops. But outside IP header is very important because this will have the VTEPs, right? So literally you'll be having one VTEP here, one VTEP here. So if the packet is going from here to here, you will basically have VTEP 1 as the source and VTEP 2 as the destination IP, right? So that's how it creates a tunnel like this, right? And that is created, and then inside this VXLAN header, what you do is, like for example, in this case, let's say I want to connect this broadcast domain with this broadcast domain, right? This is L2, this is also L2. So if I want to connect these both, I use a unique VNI ID, right? VNI is very similar to your VLAN ID, right? So you use a unique ID, say like 5000 or something like this, right? So when you use a unique VNI ID, what you're doing is, and this guy is globally significant, right? Unlike your VLANs are locally significant. Your VNI is going to be globally significant. So this is how you connect, your 4094 odd VLANs on one side with the rest of the VLANs on your rest of the fabric. So, and since this VNI ID, this number can go until how much? 16 million, right? It can go until 16 million, right? So that is why you have considerably huge amount of, broadcast domains which you can now create when compared to your earlier 4094 odd numbers, right? So what this really brings to the table is that, what the numbering, what it really changes this. I mean, you'll probably hear it in all documentation, this 4094, 16 million, all of this, right? But what is the actual essence of it is that the VLAN is no longer, the VLAN is locally significant, right? So the VLAN 10 on this guy, has no relevance to this VLAN 10. What I can do is, I can even kind of like put these both in one broadcast domain as well, 10 here and 11 here, right? What really matters is the configuration which you use to map those both together, right? So if you say that 5000 is the VNI ID, and if you map it to 10 on one side and 11 on the other side, ACI is going to take it for you, or, any data center infrastructure is going to map it that way, right? So you no longer have much significance to the VLAN number. They are just locally significant, and you can map them however you want, right? Like this. So that's and the other thing about this is, now going back to our example which we were telling, right? Now I can have customer A using 4000 odd VLANs, and I can have customer B as well using the same set of VLANs. So if a customer already has an infrastructure and they're migrating it to their data center, they really don't have to change any VLANs, right? Because if they have used VLAN 10, 15, 20 in their data center, in their older data center, they can use the same workloads now as well without changing anything, because the VLANs which we are going to give them, or basically because of VXLAN, you can really have or basically have the same 4094 over here as well, right? So that's something. Okay, so let's not get too much into it. So that's pretty cool. Let's talk about the next topic. All right, the other important thing is, probably I forgot to mention, the VXLAN which is used in the fabric, right? In case of your ACI, that is not your vanilla VXLAN, right? Which is your RFC or your regular VXLAN. It's slightly different because in ACI you have to carry all the EPG values and all of that, right? So we will probably look into that later. But just remember that the VXLAN which is there in the fabric is what we call as iVXLAN, because it's kind of slightly changed to make it work for ACI. Sweet. Cool. The other next topic is, so we have talked about the ISS, we talked about the VXLAN. That's mainly our fabric part. I think that completes the fabric part. The other thing is, let me just give you a quick intro of Anycast gateway as well, right? Because that will be useful while we talk about packet walks and so on, right? So again, coming back here, I think we've touched upon this a little before, but imagine you've got your spines, you've got your leaf, I don't know, maybe you've got a server here, you've got another server here, right? So you have servers getting connected here, right? This is your traditional ACI all connections over here, right? So now say we've got your VLAN 10, right? And you've got say, I don't know, maybe VLAN 20 here, right? Let's put a 10 over here as well. Okay, so now normally if you want 10 to talk to 20, what do you need to have, right? We talked about this earlier. We need to have those default gateway. You need to have a default gateway for 10 up here, right? So that when this host is ARPing for the default gateway, there should be someone right over here to receive that ARP and reply back, right? So you need to have a default gateway over here for the 10 VLAN, right? And by doing that, right, you'll be able to then route the traffic, I don't know, maybe to the spine and then down here and like this, something like this, right? But the question now arises, where does this gateway sit, right? If you keep it here, let's assume for a minute that you put it here, right? And say you've got your another host which is sitting here, right, the 10, and this 10 wants to talk to this 20, the traffic will have to go all the way up. Maybe let me use a different color. So the traffic will have to go all the way up here to reach this guy first, right? Because the gateway is here, and then probably, again, maybe go up the same leaf or maybe to a different leaf and come down like this, right? That's really too much extra work, right? You're basically going too many ops just to, reach your destination, right? So that's where your concept of Anycast gateway comes about, right? So Anycast gateway is all about creating the SVI, right, for a VLAN on every leaf that really needs it, right? So that the leaf can be the closest gateway, right, to route the traffic instead of sending it somewhere far away, right? So this is really what is used in ACI as well. What happens is when you configure those bridge domains, right, you basically configure your subnets, right? You're basically going to say if this bridge domain is going to be a routed subnet, and you go and configure your subnet, something like 10.0.0.1.0, right? Or you actually configure the gateway address only. So something like 10.0.1.254 or maybe 10.0.2.254 and something like this, right? Different gateways. And what happens is whenever a endpoint, right, we have talked about endpoints, right? So whenever endpoint comes and connects up to, maybe at any leaf, right, the switch basically learns the EPG, right, because that is also defined in ACI. We are basically telling the switch, look, if the endpoint comes and connects on this port on this particular VLAN, it belongs to this EPG, right? So switch knows about the EPG. And basically the epic which is there, right, which is basically a controller, will always push the gateways on a leaf, right, if it really needs it, right? So if there is an endpoint coming and being part of an EPG, which in turn is nothing but mapped to a bridge domain, right? So in that case, the SVIs which are defined here, which is basically the gateways, will basically be dropped on that particular switch, right? So if there is a bridge domain, in a network, in ACI, it is common to have multiple bridge domains, right? But if you really don't have any EPG connecting up to that particular bridge domain, then those gateways are not pushed on the leaf. So ACI basically goes with this model of storing information which is only needed, right? Storing only that information which is needed and not storing extra information. So that's the funda behind this as well. So only the SVIs or only the gateways, right, which are really needed are pushed down to the leaves, and the unnecessary ones are not, right? But that being said, with the Anycast gateway, what you do is you take that SVI, this particular SVI or the gateway is configured on all the leaves which need it. That way, this particular situation is avoided, right? Now you don't have to really send your traffic up to somewhere else to get it routed. This guy himself will have the gateway and he'll be able to directly route it to the destination. So So that's the idea about Anycast gateway. All right. So let me just summarize, or let me just put together whatever we have learned till now, so that we don't kind of we just keep a track of what's happening, right? So we talked about the basic fabric, the basic fabric network, right? Actually, I think probably I forgot to mention this. When you first bring up your ACI, right, something like this, think of it this way: you have your epic, right? So the epic connects up to one leaf or maybe multiple leaves, but there's like an initial discovery process which happens by its own. So the epic will first discover one leaf, and then that leaf, because it is connected to another spine, that gets discovered, and then this gets discovered. So it's all like a chain process, right? All the devices in your network gets discovered, and the protocol which is generally used for this is the LLDP protocol, right? Just wanted to put it out there, right? So we kind of discussed everything around the fabric network, right? We talked about things like the ISIS part, we talked about the iVXLAN part, right? And we talked also about a little bit about the Anycast gateways, right? And because that's something which kind of is important as we proceed with like packet walks and all of that, right? So let me just get that right. That is your Anycast gateway. Cool. So the next is, let's talk a little bit about the endpoint learning, right? So give me a second. All right, so when you talk about endpoint learning, let's kind of dial down a bit and talk about first the traditional networks, right? So when you talk about your traditional networks, what are the tables which those use, right? We use RIB, routing information base. We've got a MAC, right? And then we've got ARP, right? So ARP is kind of like a combination of RIB and a MAC, right? Because it's giving you relationship between IP and MAC. Anyway, so we know what these tables do. Now, but in ACI, they went and did a bit of change, right? So what they did was, let's color them, right? So the MAC and the ARP they kind of bundled it together into one table, right? So this one, they bundled it into what we call as the endpoint table, right? So this is the place where everything, literally, if you're working in an ACI environment, this is like the show command, right? Show endpoint will basically be the command you will be using day in and day out, because all your clients, all the MAC addresses, all the ARP, all the IP addresses, all of them reside down here, right? That being said, you would still have your RIB and ARP per se, right? Because your ACI is not going to be the isolated environment, right? You'll probably be connecting it to something like L3 out and stuff. On top of that, all the SVIs which I was talking about earlier, the Anycast gateways, they all will be available in the routing table as well, right? And all the BD subnets, all of that you can still see in the routing information base. Anyway, so but then and then ARP also is basically used for L3 out, right? When you want to talk from ACI out to some external network, right? That being said, but the most important kind of like point which I want to convey here is the MAC table, ARP table has been combined into the endpoint table. Sweet. All right. So that being said, let's then dial down to what the next topic would be. What are the various like if you see show endpoint, right, in one of the ACI switch, what do you see? So that's basically let's write it down, right? So what are the various endpoints which you will see in ACI? So the endpoints, the first one would be a local endpoint, right? Local endpoint is basically on a switch. So these are the leaves, right? Let's say leaf 1, this is leaf 2, and it's obviously connected to say one of the spine like this. So you've got an endpoint here, let's say some kind of a VM. So that will be your local endpoint, right? Now, when ACI learns the local endpoint, right, it basically learns your MAC and IP on a very like majority of the time, right? It learns the MAC address and IP address from the local endpoint. That's the endpoint which is locally connected, right? Then you've got also the remote endpoints. Now, what are remote endpoints? As the name suggests, on this leaf, right, the remote endpoint is basically something connected over here, right? Now, there it gets interesting. Remote endpoints, what do you learn? Do you learn MAC or do you learn IP, right? So now here it gets interesting. So if it is a routed traffic, right, then you kind of learn only the IP address, right? and if it is a bridge traffic, right, L2 traffic, then you kind of learn the MAC addresses. And what your question would be, how are we learning in a remote endpoint, right? Because local endpoints I understand, because there is going to be some kind of traffic. It could be ARP or it could be GARP or any traffic, any data traffic which comes in, the switch learns about it, right? So all the learning, everything happens in the data plane. There is nothing like a separate control protocol for this, right? So on the leaves, whatever learning happens, it happens in the data plane itself. Any data packet which comes in, I don't know, maybe some voice traffic or some video traffic, whatever comes in, the leaf learns from it, right? Now, how about the remote endpoint? So remote endpoint also, it learns via the data plane itself, right? So there will be some kind of traffic which would have come from, say, when this L1 this server wanted to talk to some server here, there would have been some data traffic which would have gone to L2 and the server 2, and from there will be some traffic coming back, right? So when the traffic comes back, right, so my guy which is sitting here, L1, will learn about either the MAC or IP, right? So again, why is this done this way? Because in ACI, like I said, one of the important thing is the idea of ACI is to know about all the endpoints, right? Not keep anything unknown, right? So that is one thing. There are no unknown endpoints. You see that everywhere in the documentation, right? In ACI. The second thing is you also want to keep information which is only relevant to you. You don't want to dump all the information and waste up the resources on the leaves, right? So that is the reason why we learn only IP address when it is L3 traffic, is because, right, when it is L3 traffic, when I say L3 traffic, what is the meaning of L3 traffic, right? So something like, say, this is 10.1.1.1 and this is 20.1.1.1, right? So when these both are trying to talk to each other, what is the first thing this server will do? The server will send a ARP to the default gateway, which is the SVI over here, right? The Anycast gateway, right? So it will send a ARP to the leaf itself, ARP to the gateway, right? If it's L2 traffic, then it would have ARP the destination itself. That's a distinction between L2 and L3. Anyway, for L3 traffic, it just learns IP because, because at the end of the day, the traffic, once it goes to the switch, right, this is the guy who is going to finally, ARP and send it down to the actual host, because it is L3 traffic, right? So the final MAC override or L2 override basically happens at the destination leaf, right? I'm not worried about the the destination MAC, right? So I really don't want, I'm going to create a VXLAN tunnel and send it to L2, and he's going to take care of the final forwarding, right? Cool. So that's one thing. So local remote endpoints, and then there are obviously a couple of other endpoints. You might see virtual endpoints, right? Virtual endpoints are mainly when, say, between the server there is some kind of a virtual switch. Cisco themselves have, AVS and AVE, couple of virtual switches, right, in this space, but it could be VMware or any other vendor as well. So when you have a virtual switch, the endpoints, when they come and connect, right, so they will appear as virtual endpoints, right? And I believe there is one more which is also called as something like peer endpoint or on peer endpoint, if I'm remembering right? So on peer endpoint, this is like something like this, right? Since we are talking here, let me just wrap that up. So imagine there are two leaves, L1 and L2, and they have some kind of let's say VPC over here, right? And say there is one endpoint connected here, but then imagine there is an endpoint connected to one of the orphan port of the VPC, maybe over here, right? So this endpoint is basically learned as what? Say on L1, it will appear as what? It will appear as a on peer endpoint, because it is on a peer, right? On a peer, which is your VPC peer, but it is also not a VPC endpoint, or it's not a normal physical, or it's not a local or remote endpoint, because it is on a orphan port, right? So that's why you call it as a on peer endpoint. But they are not very crucial for our discussion, at least mainly for the packet walk perspective. Important ones are local endpoint, remote endpoint, and need to understand that what is learned, right? And in each of the cases. Sweet. Okay, next. All right, so now let's I think we are good with the endpoint learning perspective. There is actually one more interesting protocol, which is the COOP protocol, right? So in order to explain that, probably I'll have to take a use case. So let me do that. Let me just grab this and get rid of this. All right, so what did we learn? So we learned a little bit about the endpoints. So now let me take a simple example again. You've got your spines, right? And you've got your, I don't know, maybe leaves over here this way. Sorry, I think that should come here and that is there. Okay, cool. So we've got something like this, and imagine I've got my endpoint A over here and probably something like B over here, right? So now in ACI, it's not very this is where, you know, it kind of slightly differs from your traditional networking, right? So let's just try to trace this, right? So you've got your endpoint A and B, and you know, just imagine they have their MAC address and destination, I mean IP address as, you know, let me just grab that. So you've got the MAC as A and IP as A over here, and you've got the MAC as B, and then you've got the IP as B, right? Pretty straightforward. All right, so now imagine, again, I think it's always better to compare ACI, though this is ACI, it's always important to compare, okay, let me grab that, yeah, compare ACI with your traditional network, right? So in traditional network, say A and B are in the same subnet, which is L2 forwarding, right? In which case, what would happen? So I would really need to know the MAC address of B, because I'll have to form my L2 packet, right, with the source MAC being A and the destination MAC being B, right? So what I'll have to do is I'll obviously have just my, I'll just have the destination IP, so I'll have to do an ARP, right? And I'll have to do that ARP, and the leaf one will have to flood it in all the ports, and it will reach L3, then L3 will reply back with the, you know, ARP reply, and that's how I learn about B, right? And in case of L3 forwarding, what would happen? When I say L3, A and B are in different subnet. So in that case, the source MAC will still be A, but the destination MAC will no longer be A. Rather, it will be the MAC of the default gateway, right, which is of L1, right? So the packet will come to L1. L1 will basically look at the packet, and it will see that, okay, the packet is destined to B. So it will then look at its routing table. It will do that LPM, right, longest prefix match. So it will look at the routing table, and then it will see what is the next hop, and it will try to ARP the next hop, which in this case will be a spine, or I mean whatever device is here, and it's on a hop by hop basis. ARP is done, and it is basically sent down to L3, right? So that's your traditional networks. But in case of ACI, you really, you know, a lot of this ARP is kind of like removed out of the picture. Why? Because remember I told this earlier as well, there are no unknown hosts in ACI, which means every device knows about the hosts which are connected, right? And how that happens is because, like I told earlier, the host A registers, or basically in the local in the endpoint table, right, as a local endpoint, you will find A, and similarly B also you will find it over here, right, in the endpoint table. Here you will find A, here you will find B, and obviously the IP address, MAC address and IP address as well, right? And there is another important process which happens, which is called as the COOP, right? The protocol is called COOP. COOP is a really funny, but it's a center of I think Oracle database, right? So COOP is basically one of the important things. So what happens is this leaves, right, whenever they're learning endpoints, they will quickly report it back to the spines, right? So, and once one spine gets the update, it will sync it with the other spine as well, right? But basically in your spines, you're basically going to, these are the spines, right? Or in the spines, you're going to have this COOP database, right? And the COOP database, you will basically know that, you know, the MAC address of A, the IP address of A is actually sitting where? On leaf 1, right, or behind leaf 1, right? So this information is kind of stored on the COOP. Similarly for B as well, the same thing happens here. So the COOP database will always have the information about every single endpoint, right? So what really happens is that, you know, all this ARP process is kind of, I mean, in a traditional network, I would depend completely on ARP for, you know, learning about someone else, right? But here, all of that work is reduced, right? So if I want to talk to, if A wants to talk to B, I mean, obviously we can't change the behavior of A, right? So it will probably still ARP, but once it ARPs, right, on L1, you know, I might already know where B is, right? Maybe I've already talked to him before, but if I don't, then I can, what they call is, there is a feature called spine proxy, right? So in spine proxy, I can simply send that packet up to my spine, and the spine, since it has all this cool information, what it can do is it can, right, use this information and it can send it to the right leaf. So though ARP is a broadcast L2 packet, our L1 will basically can send it as a, can send it to the spine, and then the spine can look at the leaf, look at in fact, ACI also has the capability of looking inside the ARP packets as well, right? Because if you see, just to jog your memory, how does a ARP packet look like, right? So inside the ARP you have 4 things, right? The inside ARP, this is the ARP payload or ARP request, right? So you have the source MAC, you have the destination MAC, then you have the source IP, you have the destination IP, and then this is the outer L2 header, right, which is another source MAC and destination MAC. Now these both need not match, right? Anyway, so inside the ARP request, right, I really get to know who is sending this ARP request. So I really get to know about the MACs, the client A. I get to get information about the source IP, I get information of the source MAC, and so on. So right, spines, or basically in ACI, the devices are programmed to kind of look inside the ARP request, right, to get information out of it, right? So that being said, we'll talk about ARP in detail, but what I wanted to do here is just to talk about the COOP part, right? So as the endpoints, the first step is the endpoints will go and register to the local tables here, which is the endpoint tables. These are your endpoint tables, right? And from the endpoint tables, as the clients get added to the endpoint tables, the leaves have the responsibility to go and report it up to the COOP database, which is on the spines, right? And we will see how that information which is on the COOP is kind of used in the packet forwarding, right? Basically it acts as a fallback mechanism, but we will look into some of the packet walks to understand that, right? So that's one thing, yeah, so that's mainly it, guys. So that's I think let's just try to revise what we understood here, right? So we talked about in endpoint learning, we talked that there are different types of endpoints, right? And we also learned one interesting control protocol called COOP here, right? So if someone asks you what are the control protocols used in ACI, I think you can name COOP, and obviously you have ISIS here, right? And you will also have MPBGP, but probably we will talk about that when we talk about L3 out, right? But yeah, so that's mainly. But other important thing is in ACI, the endpoint learning happens via data plane, right? You really don't have to have some routing protocol to do it, or you don't have to wait for ARP to do it for you. You don't have to wait for ARP to learn the destination, MAC address and so on. You can, majority of the times, since ACI knows everything about every single endpoint, right, that information is already there in ACI. So it's the leaf might already know about the endpoint, or destination endpoint, or the spine will know about it and is going to reply back, right? So that's a couple of things. Now let's look at some of the interesting packet walk use cases, where we will basically use all these things which we have learned here, right, to fruition. Okay. All right, so I like packet walks, right? So let's pick one thing. So let's do that. So now we are doing forwarding, right? So we'll talk about forwarding, which means we go back to our examples, which is putting in a couple of spines here, maybe spine 1, spine 2, and let's put a few of the leaves here. And now leaf 1, 2, 3, and 4. And to make our examples better, let's go and put in a VM here. Probably, let's call this as client A, with its everything is A here, right? IP address is A, MAC address is A. It is present in what, EPG1, right? Let's assume since it's the first example, we're talking about first example here, which is basically we have 2 endpoints, right? Let's say which is there in the same bridge domain and EPG as well, right? Which means our guy which is here, let's say we put this guy here in a VPC kind of a situation, and there you go, we've got B, and let's assume this guy is also part of EPG1, and obviously bridge domain 1 as well. Okay, my pen is acting up, give me a second. bridge domain 1, right? So this is what we have. So now when we talk about, let's talk about the forwarding, right? The first use case, like I was saying here, two endpoints in the same bridge domain. Let's assume that they want to talk to each other, right? So it's in the same bridge domain, and let's assume let's assume it is L2 forwarding, right? I mean, two endpoints in the same bridge domain need not be L2 forwarding. It can be L3 forwarding as well, but in our case, assume they are part of the same subnet, so they are doing L2 forwarding. Sweet. Okay, I think I missed the interfaces here. Let's do that. I think by now you would have understood leaves connect to spines, and leaves never connect to each other. Spines never connect to each other. Cool. So let's assume that starting the first use cases here, like I was saying, let's assume that the leaf 1 already knows about the destination in this case, right? We talked about all this endpoint learning, right? So maybe leaf 1 had already talked to, or A had already talked to B before. So that's how, let's assume that leaf 1 already knows about what? About this guy, right? As a remote endpoint, right? So he knows about the endpoint, which means, if you look at this guy's table, right, he will basically know that in BD1 we have this MAC B, right, and he also knows that it can be reached via, right, some VTEP, right, because it's VXLAN, right. So it knows that when I say L1 knows about B, that is what I mean. It knows that it can reach this guy using a VTEP. Now I specifically tried drawing VPC here because I want to tell a very important thing. With VPC, it might be confusing, right? Where will the leaf send the packet to? Will it be L3 or L4? So interesting thing is, between these two guys, there is what we call as a VPC VTEP is created, right? A VPC VTEP is created, just like VTEP. VTEP is nothing but just basically the leaf itself, right? So in case of VPC, because you have two leaves forming one logical switch, there is a VPC VTEP created, and all the clients behind that VPC are reachable via that VPC VTEP. So back to our discussion. So in this case, right, the table over here on leaf 1 will have this information. He'll know that your B is reachable via this. So it will create this cool VXLAN tunnel, right? And the VXLAN tunnel is going to be pretty cool, right? The outer IP is obviously going to be, it's going to be what? It's going to be from, same thing what I was saying here, right? It is going to be L1, which is VTEP, VTEP of, leaf. So that will be the source, and the destination IP is this guy, the VPC VTEP, which I talked about just now, right? So that's going to be the outer, and the inner obviously is, and obviously there is going to be a VXLAN header as well. The important thing to note is that what is the VXLAN identifier, right? What VNI will be used, right? Because it is L2 switching, we'll be using what we call as the bridge domain VNI, right? Bridge domain. So bridge domain VNI, because why? Because like I said earlier, in VXLAN, your VLAN is not the L2. In fact, bridge domain is the L2 forwarding domain, right? The L2 broadcast domain. So VXLAN basically uses, so there are two types of L2, there are two types of VNIs. One is your L3 VNI, other one is L2 VNI, right? And in case of whenever the traffic is going, whenever it is bridging traffic, right, L2 traffic, always ACI uses the bridge domain VNI ID in the VXLAN packet, right? Now what happens, the packet will basically reach my destination, right? The destination Anycast VPC VTEP, which is here, right? The packet basically reaches here, and the decapsulation happens here, and then the packet is kind of forwarded to the endpoint B, right? The return also is pretty much the same, right? It will depend upon what is there here. In this case, because for the return traffic, B has to talk to A. So here in the VPC VTEP, right, we'll have information that your bridge domain 1, right, inside bridge domain 1, we have the MAC address, which is A, and we will also have information that it is basically where behind VTEP, which is leaf 1. right? So that information will be basically present, and using that information, I can kind of like form my tunnel again, right? And send the packet back to him, right? So just to recap, right, in a L2 situation where in what we talked about just now, right, but then the other important thing is what if my L3 and or basically the VPC here, right, this particular switch here did not know about A, right? So that's a question, right? Oh, it's a very valid question. Maybe L1 never sent a packet to or maybe A never sent a packet to B before. So in that case, this guy will not have anything in the table, right? So that is the good thing about ACI, and this is really the remote learning which I was talking earlier, right? This is where the remote learning comes. And also observe that it's not a ARP packet, it's really the actual data coming in, and ACI has the capability to learn from that. So literally in that case, the source learning will basically happen in this bridge domain. So basically, in my in this virtual VPC switch, we will basically be learning BD1, right? And it will learn that, look, MAC A is reachable via this VTEP, right, on VTEP which is going to be leaf 1, right? And that's how the source learning works, right? So you don't have to worry that the leaf the VPC VTEP here doesn't know about A, because the learning happens via the data plane. So when a packet comes here, this guy has the capability to learn. Now that he has learned, when the return packet basically comes, right, from where, from my here, the VPC here will basically know, and it will be able to send it to the right place, right? Cool. So that's a very simple example, right? But let's move on. Let me just pause the video and erase this part again. So I really don't want the video to go on for long. All right. So let's move on to before we move to the second case, just to recap, what we did was, it was 2 endpoints which were in the same bridge domain, same EPG. We saw that the local learning happens here on the leaf. The local learning in the sense, A coming in registering, or basically leaf 1 learning about A. And then we also learned on the other side, right, it can also learn about A, but then that learning is like a remote learning, right, because it is learning about client A, which is not locally connected but remotely connected, but though it is remotely present, it is also learned via the data traffic, and this guy also will know about A, and the same thing happens in the opposite direction. But that was a very simple use case, because we assumed that L1 and L2 or L1 in this case, we assumed that it already knew about B, and that's how it sent the traffic along the VXLAN tunnel directly to this particular VPC VTEP. Second case is very similar as this, right? Only differences, let's assume that our leaf 1 doesn't know about B, right? Unknown, right? It's unknown. What is unknown? B is unknown, right? At leaf 1, let's assume this, right? So basically when the traffic comes in, right, and hits the leaf 1 table doesn't have any information for what? Because it's a L2 traffic, it is obviously going to do a lookup of the MAC address of what? B, right? Because it's a L2 traffic. I've been telling that. So this is L2 traffic. So in a L2 traffic, what every hop will do is they'll basically be looking at the destination MAC address, right? So, but the problem here is L1 really doesn't know about MAC P. It doesn't know where it is, which bridge domain it is, nothing, no information at all. So that is where this cool thing comes into picture, which is you have two options here, right? One is called as the flood mode, and the other one is the hardware proxy mode. So let me show you that. So on this Epic Sandbox, right, if you see here in the bridge domain, you have two options, right? You can set the two options. One is called flood or bridge or hardware proxy, right? So as per that, you can now toggle and make your behavior. So generally, I would suggest, checking out hardware proxy, because it is an optimal approach, right? And what happens in your flood, it's basically your traditional flooding, nothing very complicated, right? Only small tricky thing is, so let's talk about that. Let's talk about the two approaches here for a minute, right? Let's talk about flood to start with. With flood, what happens is, On leaf 1 it is unknown, MAC B is unknown. So what will leaf 1 do? Leaf 1 will basically send the traffic to where? It will send the traffic to your spine proxy, right? To the spines. We talked about this earlier, right? Why? Because spines already have that information. Remember, all the endpoints, when they come and register, the leaves basically go and register them back to the spine. So spines have all the information in the COOP database, right? And when the packet basically so wait, I think I was talking about flood, my bad. Not let me just get that, right? So since leaf 1 doesn't know about destination MAC B, it will act as a normal leaf, right? A normal leaf, what it would do when it is unknown unicast, it would basically, when the destination is unknown unicast L2, right, it would kind of flood the packet. So it is going to flood, but the flooding here is kind of optimized. It's not normal flooding. So what it does here is, so every bridge domain, when you set up the ACI Fabric, right, the first time when you create a bridge domain, internally there is a MAC address, so there is a multicast address, right, or it's basically called GPO address, right, assigned to every bridge domain, right. So what during the flooding, that is basically the trick which is used here, right. So now leaf 1 really needs to flood this, basically flood this particular traffic in whatever bridge domain BD1, right. So it is basically, what it is going to do is, it is going to create that VXLAN packet, but in the VXLAN packet, right, the destination VTEP, right, because let me try to draw it here, the source VTEP is what? Leaf 1, but the destination VTEP is going to be this GPO address, right, this multicast address. Got it? So now what will happen is, every leaf which really has that bridge domain, right, or which has endpoints in that particular bridge domain, right, will basically receive this particular traffic, because this is multicast traffic, right. Since L2 doesn't have it, so this guy won't receive it, whereas L3 and L4 will receive it, because they have an endpoint in that particular bridge domain, right. So the interesting thing to note here is this optimization which I talked about, right. It's not flooding everywhere, rather it is in the destination we are putting this GPO multicast address, this is multicast address, so that only those leaves where the endpoints are present for that particular bridge domain will get the flooded packets, right. And obviously once he gets the flooded packet, right, he can then reply back to the basically, since in this case it's going to be an ARP kind of a situation, right. So he can then reply back to or in this case it is flooding, basically flooding, right, because let's assume that my endpoint A already knows about B and all the ARP everything is resolved, right. So in this case it's just flooding. So basically your B will finally receive the packet because of this flooding, and he's going to reply back to whatever traffic was sent, right. So that's the only difference. That is basically your flooding, right. Now the slight difference with the second approach, which is your hardware proxy, right. So with hardware proxy, what you do is, you don't flood, obviously. So let me just get rid of that. Let me just get rid of these few things as well over here. Yeah. So with hardware proxy, what you do is, you kind of send the packet to the spines over here, because remember I told you the spines maintain this COOP database, right. So in this case, when the destination MAC is not present on leaf 1, right, because MAC B is not in the table over here, what it will do is, it will basically send the packet, right, as obviously a VXLAN packet, but it will send it to where? As to the spine. Literally it will send it to the Anycast MAC address of the spines, because it's an L2 packet, right. So the packets are basically sent to the spines. Now the spines, because of their cool COOP database, the COOP database will have all information. So it will know that this MAC address B is actually where? Behind leaf 3, leaf 4, right, basically the VPC domain. So that guy will then obviously create another VXLAN packet and send it to the right destination, right? Now if it did not find this endpoint B, right, then it will basically, if it did not find it in the COOP database, then it would drop the packet, right? So those are the two approaches, the flooding and hardware proxy, right? And obviously it is better to keep the default is hardware proxy, because obviously you see here in this case you always want to limit flooding, right? In your network you really don't want flooding. So hardware proxy is a very optimized way, because in this case you are just sending one single packet to the spine, and the spine is taking care of forwarding it to the right destination. But in case of flooding, you will basically be sending multiple copies of the packet to multiple leaves. Basically imagine if you have a lot of these floods happening, then it might congest your network. But then compared to your traditional networks, this flooding is much better, because it uses multicast, to kind of flood it within that particular bridge domain using the GPO address. All right, cool. Now I think that it's time to move towards the L3 forwarding. All right, so I just erased whatever was that. It was getting too crowded. So let's talk about the next case, which is L3, right? In this case, let's assume we have our two endpoints, right? We've got our two endpoints and they are in different bridge domains, obviously, and they are in different subnets as well. As you see here, it is 1.1.1 and the endpoint C is in 2.2.2, right? So let's assume what is going to happen now. So as usual, one wants to talk to 2.2.2, right? So first thing is the destination lookup, right? Because it is in a different subnet, what A would have done is it would have kind of arced the default gateway, right, on leaf 1, and leaf 1 would have replied with the ARP address, or basically the MAC address of the default gateway. So basically the packet would have arrived here, right? Now leaf 1 is confused. The leaf 1 wants to send this packet to C, right? And in this first use case, let's assume that leaf 1 knows about C. So how will the destination lookup look like? Because it is L3, right? So it is going to have VRF, not bridge domain anymore. So it is going to say VRF, and in that VRF, it will know about the client C, and it will also know that C can be reached via what? This VTEP tunnel, right? Remember this, we talked about this, the VTEP tunnel 2. In fact, in this case, since this guy is connected only on 4, so it is going to be like this till here, right? Sorry, here, right? So it will know that VTEP to leaf 4, something like this. So this is how the destination lookup, or the this is literally how the destination lookup looks like. So L1 will basically look at this table and it will forward the packet. And obviously if you look at the inner and outer address, the outer IP header of this encapsulated packet, VTEP will be leaf 1, this will be leaf 4, right? This is the source VTEP, this is a destination VTEP. And the VNI, what VNI will be used? Obviously we are going to use VRF's VNI, right? So it is L3 VNI which we are going to use here, because it is routing, right? So that is important, right? Now imagine, let's make it interesting. Let's say L4 really doesn't know about A, right? So the same thing, the learning which we talked about, right? The source learning happens here as well. But in this case, it will basically be, so how will the source learning happen? It will learn that in VRF, in this whatever VRF we are in, it will learn about IPA, right? This is IPA, so it's going to learn about IPA, and it will also learn that it can reach it via leaf 1. It is not going to learn about the MAC address of A, because it is L3 routing, right? So it will not learn about MAC address. It will learn only about the IP address, right? But the funny thing is, if there is some kind of L2 traffic also going to the same endpoint from this leaf, right? You might at times, if you go and check on this leaf, you might also see not just the IP, you will also see sometimes MAC address. Why? Because to the same endpoint there might be some L2 traffic also going to it, right? So in which case it will basically learn the MAC as well. But technically speaking, if there is only L3 happening between A and C, right, in that case on L4 we will just have the IP address. But the source learning which we talked about earlier applies here as well. Sweet. So this is how the learning happens, so that now when the packet comes from C to which is destined to A, our L4 can use this information which it learned, right, in the data plane, and it can then forward it on the data on this amazing VXLAN tunnel. Okay, so that's cool. Now there is one last thing which we have to learn, which is what happened. So in this case, we kind of assumed that L1 knew about the destination. So what if the same use case but it is unknown, right? Just like we did with L2, right? Here with L2 we kind of had two approaches, which is flooding and hardware proxy. But in case of L3, this is slightly different. So let me just give me a second. Let me just erase stuff. All right. So this option is one of my favorite, right? Because there's a lot of things happening in and around, a lot of moving parts here. So, but then it helps you understand ACI really better, right? All right. The first thing is we need to understand about this concept about pervasive gateway and pervasive routes, right? So let me just write it down for your benefit. We call it pervasive gateway, right? And the other one is pervasive route. What is this concept of these two things, right? So remember, we have been talking about the Anycast gateway for a long time, and that's nothing but a pervasive gateway, right? And so your question should be, on which leaves will this pervasive gateway or the SVI, the bridge domain SVI or the Anycast gateway, whatever, these are all different names, right? Bridge domain SVI, Anycast gateway, pervasive gateway, all are the same thing, right? Anyway, so your question should be, on which leaf will this gateway be installed, or APIC will install this particular gateway on which leaves, right? So that should be a question, right? So the answer to that is, if a leaf has a EPG for that particular bridge domain, right? In this case, I have a endpoint which is 1.1.1, right? And maybe this is part of a particular EPG, say EPG1, right? And let's say EPG1 belongs to bridge domain 1, right? I'm just making up stuff here, right? And let's say this particular subnet has been defined in bridge domain 1, right? Then on this particular leaf, we will have that particular gateway. Let's say that gateway is something like 1.1.1 254, right? So this gateway gets installed on this particular leaf. So ACI will install this gateway or this gateway only on the leaves which need them, right? So in this particular leaf, since we have an endpoint belonging to that particular EPG, which in turn belongs to that particular bridge domain, we have the gateway of that particular bridge domain getting installed over here. Got it? So that's something important, right? So all the gateways of that particular bridge domain will get installed here. In this case, I have just one, but if I have multiple, those also will get installed on this particular leaf, right? So that is one important point, right? And similarly here, because you have 2.2.2, maybe this is part of a different bridge domain, right? And that particular bridge domain might be part of the same, might be part of a different VRF also, right? Let's assume that is part of a different VRF. So in that case, that particular gateway, which is 254, gets installed on this guy, right? We don't really want 1.1.1.254 on leaf 4, right? Because whenever 2.2.2 wants to reach out, it just needs its default gateway. It doesn't need a default gateway of some other bridge domain, right? So that's a very, very important point, right, to understand this. That's the first part of it, which we talked just now. Just to reaffirm, only if a leaf has a EPG for that particular bridge domain, only then that particular gateway will get programmed on the leaf. Second important point is this pervasive route, right? What do you see here? This pervasive route, that is important. And this is tied to what we have discussed before, right, in the logical construct, which is the contract. Remember, we talked about contracts. Contracts are the ones which define the relationship between EPGs, or which define if a particular EPG is allowed to talk to the other EPG or not, right? So a contract is what? Tied always to EPGs, right? So what is the idea here? So in this case, if a contract is tied to EPGs, pervasive routes are basically exchanged across the leaves, within obviously the same VRF, right? So in this case, what happens is that we are basically going to have we have 1.1.1 here, and we've got the other endpoint sitting on the other side, right? So actually, let's tweak my earlier statement a bit. Let's assume that both of these bridge domains, so this is also part of, this is let me just write it down, right? Otherwise it becomes confusing. So this is bridge domain 1, right? Part of bridge domain 1, and this is part of, say, bridge domain 2. And for our benefit, let's assume that both are part of VRF1 and this also is part of VRF1, right? Let's assume this. It's always good to put it on paper, otherwise you get confused, right? So cool. So what do we have right now? We have two bridge domains which are part of the same VRF, and obviously they're part of the same tenant, right? If you look upwards, so the two bridge domains which we have here, right, they have two different subnets. One is having the 1.1 subnet, other one is having the 2.2 subnet, right? And they have the corresponding gateways, and we understood when the gateway is going to be installed. But coming to the pervasive route, right? So the pervasive route is going to be only installed, right, across the leaves only if they have some kind of a contract, right, which has been defined. So in this case, what happens is that this particular subnet, right, the 2.2.2 subnet gets installed here. So when I say it gets installed in the RIB, right? So in this RIB, you will basically find, so that's why I said, you know, when we were talking, I think, about the fabric, or maybe during the endpoint learning, we were talking about the MAC tables, RIB, and the endpoint table, right? And I said, in ACI, though everything is done by the endpoint table, there is a little bit of work for the RIB as well, right? And ARP is mainly used for L3 out. So RIB, when I said, right, little bit of work, this is what I meant, right? So this pervasive routes, right, in this case, what is going to happen is you're going to have something like 2.2.2.0/24. So this will be installed, you know, in the on the leaf 1 here, and on this guy's RIB, that is on leaf 4, we are going to have 1.1.1.0/24. Right? So that is the whole idea. So just to and you will really get to know why this is getting installed, right, when we talk about this particular third option which we have been discussing now, which is the L3 forwarding, right, especially when we have got the unknown destination, right? So you'll really understand why this particular route is needed. But let's pause that for now. I just want this point to, you know, kind of go across, where when a pervasive gateway is installed, right, and when pervasive routes are installed, right, and pervasive routes are always exchanged across the leaf, but within the same VRF, right? It's not inter VRF. The other VRF, I mean, if this particular 2.2 was in a different VRF, then we would have not done this, right? We would have not exchanged the pervasive routes. If they are in the same VRF, which is in this case VRF1, we have two bridge domains. We've got you know, two different subnets which are defined for those bridge domains. In that case, ACI looks at it and sees that, okay, maybe A and C, they have to talk to each other, right, because there's a contract defined. So what I'm going to do is I'm going to pick the pervasive route and I'm going to just install a route in the RIB of each of the leaves, right, which have those endpoints. All right, so let me just give me a second. Let me just get rid of this so that we can discuss the final forwarding now. All right, so the final use case here is, so in L3 forwarding, let's assume that you know, A wants to talk to C, and the packet has reached L1, the leaf 1, because of the default gateway, right? So A has ARP the default gateway, and L1 responded, and we send the packet to the pervasive gateway or leaf 1, right, whatever. Leaf 1 has received the packet. Now, but the leaf 1, right, doesn't know about the destination, 2.2.2, it doesn't know about the destination. Why? Because that endpoint table which we have here, right, remember the endpoint table, let's assume that it has not learned, right? So C, there is nothing, right? So what will happen? Now, in case of L2 forwarding, remember, whenever the leaf did not know what to do, it would either flood or it would do hardware proxy or spine proxy, right? So it would send it to the spine and, you know, help resolve. So in this case, currently, how will it do? Because this is L3, right? So what really happens here is that this particular RIB comes into play. So in ACI, the order of operation is first check endpoint table and then go for RIB, right? So this is the order of operation. So now what it will do is it will look at the RIB, and in RIB it will find this route 2.2.2. Remember, we have installed this, and this is the really use case of installing this, right? Because they have a contract between you know, this particular endpoint group and whatever the endpoint group is here, right? Because that endpoint group has a contract, ACI has you know, installed this particular pervasive route, and because of this, now for this particular pervasive route, the next hop, right, which will be installed will be this Anycast of the spine, right? That will be installed. So this will be the route, and this will be the next hop. So what will happen now is the packet will be sent to the spine like this, right? So any cast of the spine it will be sent to, and then what happens, obviously, so this was basically, this entry is installed here just to kind of like, send it to the spine in case, the reason is, think of it this way, right? What if we have this particular endpoint trying to talk to someone else, right? Let's take an example, maybe 3.3.3, right? Let's assume 3.3.3, and 3.3.3 is not part of the ACI. Let's say it's part of some other network somewhere outside, right? So now we don't want to really send all the traffic to spine, right? We don't want to simply overload the spine with like a lot of unnecessary traffic, right? So the use case of this RIB route is just to validate that if this particular subnet, right, is present in our bridge domain, right, and if there is a contract between 1.1 and 2.2. So it all goes back to our earlier statement, right? In ACI, they have tried their maximum to make sure, right, only relevant stuff is stored and relevant traffic is sent, right, so that we really don't have anything unnecessary going on in ACI. That's the funda, right? So that's why here as well, if there is some traffic going or destined for 3.3, it will be dropped here directly, because or if there is a default route put in RIB, maybe it will send there, but ACI will immediately understand that, look, this 3.3.3 is not a valid subnet in my bridge domain, as well as it is not a valid subnet to which I am supposed to send traffic, right? Maybe in this case, right, it is not 2.2, so I'm not going to kind of encourage this traffic, and it will be dropped, right? So the whole reason of putting this guy over here is to make sure this particular traffic is not dropped and send it to the spine proxy, or bypass it to the spine proxy. Now once it comes to spine proxy, it is pretty straightforward. Just imagine, but because this is a layer 3 traffic, the VNI will be the VRF VNI, right? It's a L3 VNI, that's it, the identifier which is used in the VXLAN packet. So once the packet comes to the Anycast spine, this guy will do two things. He'll either look up in its COOP table, right, that COOP database which we talked about. He'll look up to check where is C. Now if C has already registered, or leaf4 has already registered the C to the COOP table, then he'll directly create a VXLAN packet and send it directly to leaf4, which will like this, right? He'll directly send it to leaf4, which will then send it to C. But there could be another question also. What if it is not there in the COOP table, right? So there is another interesting thing which happens here, which we call as the ARP gleaning, right? This is pretty cool concept as well. So what happens in ARP gleaning is, spine will send an internal message to the leaves telling that, look guys, I tried checking my COOP table, but I don't know who C is, right? And this is a very interesting use case for silent host, right? Silent hosts are those hosts which really don't send any kind of traffic. As a result, the leaf would have not known that C is connected to it. As a result, leaf would have not registered that particular host to spine as well. So really no one knows about C in this full fabric, right? So how do you take care of that? ARP gleaning is one of the interesting mechanism for that. So what the spine will do is it will send an internal message to all the leaves saying, look, for this particular bridge domain, I have received some packet, right? Currently I have received it from this particular bridge domain, right? And currently I don't see a particular, I don't see any kind of host, right, with the IP address of 2.2.2. So let's do ARP glean for this particular host. All right, so there's so the ARP glean message is basically sent to the leaves, and the leaves, what it will do is it will look at this particular target, which is 2.2.2, and it will see if this particular 2.2.2 is present in its bridge domains, right? It's part of any of its bridge domain subnets, and if it is there, then it will only create the ARP request. Think of this as like fake or dummy ARP request, right? So these are created by the leaves themselves. So they will create this amazing ARP request, and they'll be sending it down, and that time the C will respond to it, right? And that's how leaf will learn that, look, okay, C is connected to it, and then it will obviously report back to the spine, so that next time a packet comes, everyone will know about C, and eventually leaf 1 also will learn about C, and that's how the whole communication happens, right? So there are a lot of moving parts here. That's why I said this is a very interesting use case to understand ACI much better, right? The L3 forwarding, especially when your destination is unknown, right? So we talked about pervasive gateway, we talked about pervasive routes, we talked about how that pervasive route is really useful, right, to optimize the ACI behavior. And the Anycast spine is the next stop, and once it goes to the next stop, there are two options again. Either it can be COOP, or because of COOP it can directly forward to the destination leaf, or if it is not there in the COOP, then we can do ARP gleaning. ARP gleaning is where the spines basically send a message to the leaves, and the leaves will take over by creating this dummy ARP request, right? So the source IP for this ARP request will be the gateway address, right? Just remember that. So they will create this ARP request with the with gateway as being the source, and this ARP request will be sent to, only those leaves which have this particular IP in its bridge domains, right, or subnet in that bridge domains will generate this ARP request. So everywhere, right, in ACI it has been designed in such a way that you eliminate unwanted traffic, right? So that has been the funda everywhere. So that's pretty cool. So yeah, once the ARP cleaning happens, that everyone comes to know about this silent host, and that's how we get everything, we get the ball rolling. Sweet, awesome. All right, so before we proceed, let's just review whatever we've covered till now, which is the L2 forwarding and the L3 forwarding. All right, so here are a couple of flow charts which will help us understand, because we talked about a lot of moving parts, right? So it's very useful to put it in a flowchart format to understand, the whole funda, right? So let's do with the L2. So this is the one at the top. This is our L2, and this is our L3, right? So when you're talking about L2, you can see the packet is coming in. Then we decide if it's a L2 or a L3 packet. And how do we do that? We do it based on, so packet has come in. Sorry, let's get rid of that. Use a different color. Yeah, the packet has come in. Now you decide it is L3 if the destination MAC address, right, of the packet. So this is the packet entering the leaf, right? So if the packet which is entering, this is the leaf, and this is how it is entering. If the packet is destined to the gateway, right, gateway of the leaf, or basically if the destination MAC address is MAC address of the gateway, then it is a L3 packet. So we'll talk about L3 here in the next section. Now if it is not, then it is a L2, right? If the destination MAC is not the gateway MAC, then it is L2. Now in L2, as soon as it comes here, you have two options. Either the leaf knows about the destination MAC in its endpoint table, in which case we basically go this path, we come here, and the destination MAC, it can be on the local leaf itself, in which case it is going to act as if it's a normal, switching, right? How a normal switch would work. Similarly to that, the endpoint table will tell that, look, this particular leaf is connected to yourself, this endpoint is connected to yourself, just forward it there. So this would happen. If it is not on the local leaf, then it might be on the remote leaf, right? So it will be as a remote endpoint. It will appear in your endpoint table, in which case you forward it to the egress leaf using a VXLAN tunnel. Now the other option is coming here where the leaf doesn't know about the destination MAC. In that case, we have two options, right? We can either flood or we can do hardware proxy, and this will depend upon your configuration in the bridge domain. Now, if it is flooding, then it will flood inside the bridge domain, because the bridge domain is the L2 forwarding domain, right? And the packet would finally reach your egress leaf, and that would then again flood it, because all the endpoints on that particular leaf has to get it, and the correct endpoint will then reply back, or it will receive the packet, and it will rest of the guys will discard it, whereas the actual endpoint will receive it, and it will start replying to the original source. And during all this process, obviously the source learning will be happening, right? Source learning would have happened anyway. So in the other option, which is the hardware proxy, we don't flood it, rather we send it to the spine, right? We send it to the spine, and the spine will look at its scoop database, and in that, if it finds the destination MAC, then it will forward to the egress leaf. If it doesn't, then it will drop it, right? So this was the complete workflow of L2. Now L3, when we talk, again, the packet is coming in, right, into the leaf from the endpoint, and the destination MAC is equal to the ACI MAC, or in this case, when I say ACI MAC, it is the SVI or the gateway MAC. So that is how you understand it is a L3. So basically, what we are doing is we are doing a continuation of this. Whatever we did here, we are coming here, right? So the no part is coming here. Literally, we can stitch both of these graphs together, but I've kept it separately here. Anyway, so we have come here. Now, there are two options here. So if the leaf knows the endpoint, right, then it is pretty straightforward. Then we will again check if the endpoint is on the local leaf itself, in which case we will forward to the local leaf. If it is not, then we build that VXLAN tunnel, right? But this time we'll be using the VRF VNI, right? In the above, we would have used the bridge domain VNI, but here we'll use the VRF VNI, and we'll create the VXLAN tunnel and send to the egress leaf. Now, if that is not the case, right, where what I mean is the destination, I mean the leaf really doesn't know about the destination IP, then in that case, we come here. Now, what the leaf, does the leaf have the BD subnets, right, for the destination IP? So this is relating to that pervasive gateway and the pervasive route which we talked about, right? So the leaf will check, look, I have received a packet for this destination IP. So in our case, it was 2.2.2.2, right? So it will try to check if this one has a pervasive route, right, in its RIB. If it finds a pervasive route, it means that, you know, it is, does the leaf have the BD subnet? So it means that that particular subnet is present, right, and it will send it to the Anycast spine, right? It will send it to a spine proxy, and spine will then again do two things. It will check its scoop table. If it finds in the scoop table, then it will forward to the egress leaf. If it doesn't, then it will do, it will either drop or I mean, it will drop the actual packet, but it will also initiate this ARP gleaning, right? Remember, we talked about ARP gleaning. The ARP gleaning will get initiated so that, you know, when the next packet comes, everyone will know about who the endpoint is. So this is one approach. The other approach is if that particular subnet was not in that, you know, RIB, right? The pervasive route was not there. Then what will happen is, then the leaf will think that, okay, this is not part of the ACI fabric itself, right? So it will then understand that it might be present in the external network. So you have ACI over here. Imagine your whole leaf spine, everything is there, but this guy might be connected to some external network, right? So it will think that maybe this particular IP, whatever you are trying to reach out to, maybe the 2.2.2 maybe is over here in the external network. And we will probably talk about this external network later in the series, the L2 out and L3 out. But basically what the leaf will think is, okay, it might be in the external network. So it will check again the RIB, and if it finds some kind of a default route or something, right, or if it finds an external route itself for this 2.2.2, then it will you know, forward it to that egress leaf as per routing table. If it not, it will drop it, right? So that is mainly the whole workflow of how the whole L2 and L3 forwarding works in ACI, right? Now, again, I would suggest take this as your initial you know, blueprint, and then fine tune it more, because, you know, in ACI there are a lot of options, right, which you can knobs, which you can turn on, turn off, and you can again alter this full behavior, right, depending on what combinations of those knobs you use. So use this as an initial blueprint and then try to play around with it as well. All right. Okay. So I think we still have a couple of things to discuss here. All right, so we'll talk a little bit on ARP itself, right? Because ARP is a very important traffic, right? So we talked about the third one, so we'll go to the fourth one, which is mainly ARP, right? We'll just talk a little bit about ARP, because ARP is a very important traffic in any networks, and we need to really understand how our ACI interacts with ARP, right? So that being said, let me use a different color. So in a traditional switch, what happens, right? So in a traditional switch, you have a ARP request coming here like this, right? And you're probably going to have a bunch of endpoints, right? I know, maybe endpoint A, endpoint B over here, and the switch, and imagine all of them are in the same VLAN, right? So the ARP request will be flooded, right? Because the destination MAC address of ARP request is all Fs, you know, it's all one, sorry, or all Fs also you can say, right? So switch will basically flood the packet on all the ports, on here as well as here. And the right guy will then respond back with ARP reply, and that's how, you know, so it's all flooding, right, in a traditional network. But in ACI, this flooding is really not needed. If you are using ACI in its default behavior, the flooding is not needed, because see, imagine you have two spines, you've got your leaves over here, right, and you've got all your amazing connections. This is good. So why is the flooding not needed? Reason is because, say you have a host here, you have a host here, you have A, you've got B, and A wants to talk to B, right? Remember, we have talked about this endpoint table, right? So if leaf 1 already knows about this B, right, and it knows that this B is connected to leaf 3 over here, right, over here, so it will have in its endpoint table that B is connected to leaf 3, right, and it would have learned via the data path already, right. So if it already knows that, right, when the ARP request comes in, right, when the ARP request, though it's a broadcast packet, when it comes in, what the leaf can do is it can send, it will look at the ARP packet in itself, right. It will look at the ARP packet, and we have talked about this. The ARP packet has the source IP, destination IP, source MAC, destination MAC. So it will look at the destination IP, and it can figure out that, or I mean, it look at the destination MAC and can figure out that this particular packet is actually, or this particular host B is actually connected to L3. So instead of flooding this particular ARP, right, it can send a unicast ARP like this, right, because it can encapsulate that the ARP request and VXLAN can send it directly to L3, and then your L3 will obviously forward it down the chain here to B, and then there will be a reply coming in, and when the reply comes, even L3 would have learnt about A, right, in its endpoint table, so it will also send via the VXLAN tunnel back here, right. So understand how the behavior is different. In your traditional network, it will be flooding. ARP requests are always flooded in the L2 domain. But here, the interesting thing is in ACI, the fabric is mainly L3, right? Between the leaves and spine, it is L3. So the leaves can't like flood it on those directly because L2 packets basically cease to exist in the L3 domain, right? They are dropped because this is L3 domain. So instead, leaves, what they do is they use the intelligence which is built into them, mainly with respect to the endpoint table, right? And if it already knows the endpoint, then what it can do is it can send a unicast, right? So the ARP broadcast kind of becomes unicast, and it can be sent to the direct. So it will be send as a directed unicast, and then it will get the reply, and that's how the learning happens, right? So that is a major change. But then I also have a flow chart here to talk about how the various other options play out in case of ARP as well, right? Similar to how we talked about the L2 and L3, there are many other options as well. So let me just take you guys through that as well. Okay, so here, so we've got the ARP packet coming in. So let me use the color again here. So we've got the ARP packet coming in. It's a different color here. All right, so we've got the ARP packet coming into the leaf, right? So what I mean is you have a leaf here like this, and you have a client, right? Maybe some VM or something, right? And it is connected here, and there is a ARP packet. So ARP packet, if it is coming in, it can be two things. One is the ARP packet is destined to the leaf itself, which is the destined to the default gateway of the leaf, in which case it is a L3 packet, right? So that is why they are saying, is the unicast routing enabled in bridge domain, right? So if the unicast routing is enabled, yes, and if the ARP is for the ACI's pervasive gateway, and that is also yes, then it means that the leaf will intercept that particular packet, because if the ARP is destined to this guy, the leaf will reply back, right? Because obviously the leaf will know about the ARP request, and it will know that it has to respond, so it will respond, and this is mainly your L3 forwarding from here, right? So the packet will come to leaf, and then it will basically continue to the L3 forwarding, which we talked about earlier. Anyway, so apart from this, let's go back here. So if the unicast routing is not enabled, then it is no, in which case it is just you're using that bridge domain only for L2 flooding or L2 forwarding, right? Unicast routing is especially very important for routing in a bridge domain. If you don't enable that, you're just using it as a switch, and you're doing only L2 on it, right? So in which case the ARP packet will in which case as soon as you disable unicast routing, the ARP flooding will get enabled, right? ARP flooding is very similar to how our normal switches work, right? So all the intelligence, all the cool things about your ACI are lost. So that's why it will start flooding, and it will obviously flood. Remember, we talked about this before as well. The flooding in ACI is not like normal flooding. It is still optimal. It is still better than the normal flooding. So the flooding also will happen using the GPO, right? The GPO address. That means the flooding will happen only in the bridge domain. It won't happen everywhere. So the flooding happens in the bridge domain, and the flooded frame, basically reaches the egress leaf, and that will again flood it downwards to all the endpoints, and the right endpoint will reply back with the ARP reply and so on, right? So this is a very rarely used approach, I would say. Generally people go and enable unicast routing. But again, yeah, if your requirement is this, probably this is something you want to explore. Now, if you have enabled unicast routing, we talked about the L3 part. This is done. Imagine the ARP is not for the ACI gateway, right? It's not for the gateway, in which case this is, let me get rid of this. So it is not for the gateway, in which case it clearly means that it is more like a L2 forwarding, right? Because if this guy is creating an ARP request and it is not for this guy, then it means that he has created the ARP request for some other VM, right? Which is, this is VM A, then this is VM B. Maybe he has created an ARP request for the VM B here, right? Because he wants to talk to B. So that is where, we come across this option over here, right? So we have come here. Now what happens is Leaf will check if ARP flooding is enabled, right? So in when you create this bridge domain, you have an option to turn a knob. You can enable that particular knob, right? If you enable that knob, then your ARP flooding will get enabled, and whatever we talked about here, right, in the previous whatever we talked here, this whole idea about the unicast ARP, right, that all of that is lost, right? So basically, if I have to put this in a short way, ACI gives you the flexibility to allow flooding of ARP to work, right, like it works in the traditional networks, right? If you want to do that, please go ahead and do that. But also remember that there are some advanced and intelligent ways to prevent that, right? And if those are really those work in your network, then it is always better to use those optimal methods. But that being said, it allows you to flood as well. So if you turn on this knob, right, if ARP flooding is enabled, then yes, then it will get flooded, very similar to this, right? It gets flooded within the GPO, within that particular bridge domain, and then the flooded obviously you'll get a reply from somewhere if that particular client is there. Now, if you have not enabled ARP flooding, right? So this is that optimal approach which I'm talking about, the ACI optimal approach, right? So if you have not enabled ARP flooding, and by default, I think it doesn't, it is disabled. So default, you'll be thrown into this option itself. So if the ARP flooding is not enabled, then the Leaf will check if it knows the target IP address in the EP table. What is this target IP address? I talked about, in the ARP request, right? Inside the ARP request, you have the source IP, destination IP, source MAC, and the destination MAC. So it will look at this destination IP, right? The Leaf will look at the destination IP in the endpoint table. If it finds, then it will forward it to the egress leaf. This is that unicast directed ARP request which I was talking about earlier, right? So it will directly send it here, and then the egress leaf, sends it to the target, and you get the reply, and all of that cool things happen. And if the Leaf does not know the IP address in its endpoint table, then it will be done as a spine proxy, right? So it will send it to the spine. Does the spine have it in the coop? If yes, amazing. The spine will send it directly to the leaf, destination leaf. If it is not there in the coop, then what? The ARP gleaning process, right? That packet will be dropped, but then there will be a ARP gleaning initiated, and we will basically get to know if it is a silent host. We'll get to know about it soon, right? So that's mainly it, guys. I mean, it's nothing complicated. This is just a flow chart which shows what happens when ARP request basically comes in, because ARP is also very important to the network, right? One of the most important packets. All your that is literally the first packet which sometimes comes into your network, right, from any of the clients. So it's kind of important to understand what happens when a ARP is seen in the network, right? So this was the complete funda here. But just to remember, right, if this is kind of like the ACI's default behavior, this part, right? But then ACI also gives you the mechanism to go back to your traditional switch behavior, which is this one, right? And this one is obviously all L3 stuff, right? This is literally nothing to do with ARP mainly. This is literally L3 stuff. And this one is seldom used because, if you do this approach, right, then we are not really enabling routing in your bridge domain. That is like disabled, right? So there are just like any other packet, ARP also has like such combinations, 3 main combinations as you see here, and that's how you play around with it. All right. So I know this video is probably getting too long, but still I just want to cover everything as much as possible, right? So I'll probably put the timestamps for different sections so that you can just go and read about only those sections, right? But anyway, so let's come back, and so we have talked about this. Let me just get rid of this one sec. All right, so next is we'll talk about multicast a little bit, right? We'll just look at the surface of it, right? Probably let's put it here. We're gonna talk about multicast. All right, so when you talk about multicast, the problem is, again, let's go with our traditional topology, right? Couple of spines and few leaves here, right? So we've got something like this going on, right? All right, so one way to do multicast would be to get the ingress leaf to create multiple copies, right? So let's say I have my bad. Okay, so I have, say, I don't know, a multicast source here sitting, right? So one way to do it would be to get this guy to create maybe one copy here and another copy here and so on, right? So get the ingress leaf to create multiple copies. But this is not really scalable, right? Imagine you have multiple sources, multiple leaves. That's going to create a lot of traffic, right? A better way would be to kind of send it to our amazing leaves, to our amazing spines which are here, right? So from here, send it to the spines, right? And let the spine do it for you like this, right? And remember, spines are more powerful devices, right? They are like your chassis based devices generally. They are more powerful, they can handle it, and that way you don't waste the resources on your leaves, which are very important, right? Because your endpoints and clients connect up here, right? So now to do this in a more optimal way, ACI brings in the concept of FTAC trees, right? So what it really does is, let me just get rid of that. Okay. So what it really does, the idea behind the FTAC tree, right? It still is the funda is still the same. That is, the leaf will send the traffic to spine, but then the spine should really forward this traffic to all the deserving leaves, but also make sure that there are no loops, right? Because if there is loop, then again, that also is a huge problem. You don't want to have a multicast loop in your network, right? So in order to create a loop-free topology in your fabric, right, mainly for your multi-destination traffic, right, you use FTAC tree, right? So how does it really work? So in this case, basically what really happens is, one of the spine, literally your ACI I think supports between 12 and 16 FTAC tree. I'm not sure of the exact number. I think back then it was 12. I think now probably it supports 16. But what is this tree concept, right? So what ACI does is, it will pick one of the spine as a root, right? Root of the tree. So this FTAG is nothing but a tree. It's like a tree structure, right? So which with basically one device as the root, right? Basically like STP. You can think of it as STP for multicast traffic. So you'll have a root, right? And that guy will be at the top, right? And he will basically forward the traffic to all the leaves one by one, right? And so in this case, it's going to be something like this. Let me show you. So it's going to be, maybe let me use a different color. So the traffic will go from here up till the spine, right? And this guy is the root of one of the FTAC tree, right? And in the FTAC tree, it will be defined this way. It will be defined that, okay, for this particular FTAC tree, we have to send the traffic to this leaf, and you have to send one more copy here. And how do you send it to maybe one of the leaf here, maybe from here to here, like this. So this whole pattern which I've drawn here, that is kind of like defined and stored in this FTAC tree. Now this is just one FTAC tree. So this is why I'm saying I think I'm just going to go with 12 for now, but you can check the documentation. It might be 16. There are different FTAC trees which you can define. And you can define probably one of the spine to be root for one of the tree, and you can define maybe another. You can define this guy to be the root for another tree, like that, right? So you can define up to 12 to 16 FTAC trees, and all of them will be rooted at the spine, right? And why do you have this 12 or 16 FTAC trees? Because when you have lot of multicast, traffic coming in, right, from multiple servers, right? So different leaves can use different paths, right, different abstract trees, so that you don't send all the traffic to spine 1 or you don't send all the traffic to spine 2, right? In order to prevent that congestion, what you can do is, what it literally does is, when the traffic comes in the spine, or actually when the traffic comes in at the leaf, right, there will be some kind of hashing which will be done, right, based on the source IP, destination IP, source MAC, destination MAC of that particular flow. Some kind of a hashing will be done and the leaf decides which FTAC tree to use, right? So that way we are making sure that our multicast traffic reaches the right place, it is not looped, as well as we are also kind of load balancing, right? We are not congesting one of the spine, or we are not congesting one path with too much traffic. Rather, we are making sure that it is getting uniformly distributed throughout the network. All right, so there's one more important thing, right? So let me just okay, I've been telling that one more important thing for a long time now, but yeah, so in multicast, once you understand that it's based on FTAC trees, there's one more thing I wanna explain here before we close multicast, right? So going back to the same diagram, right, you have, I don't know, maybe couple, let's put probably 4 of the leaves here, and you understand the connectivity by now. I'm not going to focus much on it. So you've got, say, one of the multicast source here, right? So, and as we talked earlier, so the traffic is going to come here. Maybe this guy is the root, right, of that particular FTAC tree, and he's going to decide that the traffic has to flow. Now imagine you have hosts here, you have the multicast receivers, right, on leaf 3 and leaf 4. This is leaf 2, this is leaf 1, right? So there are 2 options for multicast when you configure it in your ACI. One is called flooding again, other one is called optimized, and by default it is in the optimized, this knob is selected, right? So in flooding, what happens is, as you see here, the leaf 2 doesn't, so these are the receivers, and this is the multicast source. Right now you see the leaf 2 doesn't really have any kind of multicast receiver here, so which means it would have not received any IGMP join, right? So but then, because you have selected flooding here, what will happen is, right, the FTAC tree, as per the FTAC tree, it will forward it to L2 to leaf 2, and this guy also will flood it downwards. It will obviously be sent to 3 as well and 4, because they are also part of the FTAC tree and they will also flood it down, because in their case, they have received multicast joins, right, IGMP joins, they would have received this joins. But I wanted to concentrate here on this leaf 2, because he has not received any IGMP join yet, because flooding is enabled. The multicast packets will be sent down and flooded down this particular leaf, right? Now that's only difference between flooding and now optimized is that this will still happen, because they have leaf 3 and 4 has received the IGMP join, so this flooding or forwarding down will always happen. But on leaf 2, since we have not received the IGMP join, and you have selected optimized approach here, right, in your bridge domain, when you created the bridge domain, right, this leaf 2 will not forward it down, or will not flood it like it did in the previous approach. Why? Because there are no multicast receivers, right? So that's why, again, let me reiterate the point. In ACI, right, they have made sure they have implemented, or they have designed it such a way that we are reducing all the unwanted traffic as much as possible, right? So be it unicast, be it multicast, be it broadcast, be it ARP, L2, L3, everywhere, right, they have designed it carefully and tried to make sure that we limit flooding, we limit all the unwanted traffic. All right, so the next topic we want to discuss here is something which comes along this, sorry, this is 6th one, right, my bad, let's just do 6. Okay, it's going to be policy enforcement, right? So now we have kind of understood how the whole traffic flows around, how ACI handles different kinds of traffic. So it's time to kind of put all this information together and get to the meat of it, which is kind of like because at the end of the day, we are really not concerned about how ACI is forwarding, because it is all doing it itself, right? All of this information was for you to understand it better, but you're really not configuring any of it literally on the switches. All the ACI is doing it all of it by itself. The actual thing which you will configure is the policies, right? The contracts mainly, right? All this interface policies and all of that, and finally the contracts between the EPGs is what you would be configuring. So how is that really getting implemented? When I say EPG A is not allowed to talk to each EPG B, what I really mean by that, and how does ACI really enforce that? That's what we'll be looking here. So we've got, again, going back to our amazing diagram. I think I'm getting better at this now, drawing it so many times. Anyway, so we've got these guys, right? And let's assume that we have, I don't know, maybe a couple of bridge domains, right? Let's say we have had a bridge domain 1, bridge domain 2. We have some EPGs here, right? This is A, this is probably B, this is probably C. And we have talked about this before. A and B has to talk to each other, then you need a contract between that. Let's say B and C also has a contract, right? And let's say, you know, A and B, they don't have a contract right now, right? A and C have a contract, C and B has a contract. So we've got that, and say we've got, let's go with A here, let's go with B here, right? I'm not really concerned about C for now, right? So ideally A and B should not be able to talk to each other, right? Because they really don't have a contract, and that's the whole idea between EPGs, right? Now we have learned about how A and B can, you know, from a networking perspective, we have understood how A can talk to B, right? How the communication happens, right? Without thinking much about contracts till now, right? We have just understood how A can reach B, right? That's all what we did here with the L2 forwarding, L3 forwarding, ARP and multicast and all of that. But now comes the very important part. Good, okay, it's okay, they can reach each other, but can they really talk to each other, right? Where is our policy getting enforced? Now, how this works is, as the endpoint A comes and connects to ACI, right, we know that it gets put in a particular EPG. And EPG, we know that generally it is based on port and VLAN, right? I'm not saying exclusive to this, because there are other, you can also do it based on IP, source MAC and so on. But let's consider the common case, which is port and VLAN. So based on a particular port and based on the VLAN which it comes in, right, it gets put in a particular EPG. And that's how ACI is able to understand that it's belonging to EPGA, right? So similarly here as well, when B comes in, the ACI will understand that it belongs to, this leaf will understand that it belongs to EPGB. This guy here will understand that this particular belongs to EPGA, right? Now, if the leaf one over here, sitting over here, already has the information about B, right? If it already has the information about B in its endpoint table, right? If it knows the EPG to which B belongs, right, then the corresponding contract information also will be pushed here on A, right? That way the enforcement can happen here itself, right? Or what I'm getting to it is, if leaf 1, which is here, already knows, right, about the contract, right, between A and B, in this case, right, the A and B, then the enforcement will happen here and the packet will get dropped here itself. Right, you get the point? So that is one approach, right? But then for that, A and B, right, should have, basically the leaf 1, right, should have that information, right, about A as well as B for the enforcement to happen. Now, if that information about B is not there, which is in this case very common because they are part of a different bridge domain entirely, and there is not even a contract between them, right? As per, I mean, by default it is deny, right? Because if there is no contract, it will literally not allow two EPGs to talk to each other, which means it's like a default deny, right? So that being said, what will happen here is the packet will have to go to B, right? And how will the packet, what is the packet flow? Obviously, it will go to the spine and from there it will go, right? I mean, it's the VXLAN tunnel will be created to the B, but then in the underlay, the packet will be, because this is the next hop, right? There is no direct connectivity to the leaf. So it will have to go to spine and then go to the leaf. Now, always remember that there is no enforcement which happens at the spine, right? Spine never takes part in any kind of policy enforcement, right? you just use spines for doing all your spine proxy, or you use it for your underlay and all of that, but it will never do any kind of enforcement. But at the same time, when this leaf, right, sends this packet, it would have, so in the VXLAN or the iVXLAN header, right, there is a separate field for this, where it will put this source EPG information, right? The source EPG information will be put in that particular packet, right, and sent. So that way, when B receives the packet, right, it can look at the packet, it can look at this, when it is doing the decapsulation, it can look at the source EPG information, and then it now knows that, it knows that this packet is destined to B, and it will have information about, what? It will have the information about the B's EPG and its contracts as well. So now the enforcement can happen here, right? So having reachability between A and B is a separate thing, but what really determines the communication is the policy enforcement, right? If there is a contract and if the contract says allow, then obviously the packet will be allowed. But then if there is some kind of a deny, right, or maybe in this case A and B are not allowed to talk to each other, then the leaves are the ones where the policy enforcement happens, right? If the leaf already has the source and destination EPG information and the contract information, then the enforcement can happen at the ingress itself, or the leaf will basically tag, or when it sends the iVXLAN packet, it can send the source EPG so that the enforcement can happen at the destination. Sweet. Hope that is clear. All right, so looks like we have finally come to the end of the whole discussion. At least these are all the things which were on the top of my mind to discuss with your ACI. Mainly, I think this is literally the meat of ACI, right? Whatever we discussed today. And obviously, this is not the end of it. What I'm going to do quickly is let me show you the epic ones. Yeah, so on the epic, let's go to tenants. Let's pick one of the cool tenant here. I don't know, maybe the first one. And in the tenant, let's hope that there are some bridge domains which are configured. Yes, someone has done it. So let's go to that guy. Let's go to policy, right? So everything we discussed here, all the knobs, right, they are here. So we discussed the L2, flooding and the spine proxy. That is here. You see the default is hardware proxy. And we have the ARP flooding knob here, right? By default, it is, you see it is unchecked here, right? So this is the ARP flooding. You can enable it or disable it. Then we talked about what else? IPv3, we talked about this multicast, right? Flood and optimized. You can see that over here, right? Sorry, this one, the second option, sorry. The L3 unknown multicast, we talked about that as well. We did not talk much about IPv6, but it is very similar, right? The knobs are very similar. Same as, IPv4 multicast, it's very similar to IPv6 multicast as well. We did not talk about only one thing, I guess, which is multicast destination, multi-destination flooding. But the idea here is, if I have to quickly tell you, it is, I have been telling you that VLAN is the L2 broadcast domain for ACI, right? But if you want to change that behavior, this is a knob. Again, very rarely you use it. If you want to change that behavior, you use it here, right? This is flood-in bridge domain. That is the default one. But you can also go for flood-in encapsulation, which means this is nothing but going back to your earlier traditional networks, which is making your flooding happen in the VLAN itself and not the bridge domain, right? So those were all the knobs. I just wanted to quickly show you where you will find them, right? It's basically under the policy of your bridge domain. Cool. So just to summarize, stuff what we revised or which we went over today was that we talked about Fabric to begin with, right? Let me just increase the size of this a little bit probably, right? So we talked about the Fabric, right? Initially, how the Fabric comes up, how the ACI, VXLAN and the Anycast gateway and all of that, right? We talked about how the IP addresses, the IP unnumbered is used, and we talked about the infrastructure VLAN and bunch of those, right? So how the initially first time when you boot up your Epic and your how it discovers your network, that is basically done in Fabric discovery part. Second is we learned about endpoint learning, how the leaves and spines, they learn about the endpoints which are connected, to the ACI, and we talked a little bit about COOP as well. we learned the very important thing in ACI. All the learning happens in the data plane. Except the spines, they learn about any endpoint via COOP, which is the control plane, right? But all the leaves, they learn about the endpoint via the data plane. Then we learned the very important part, forwarding, or let's say packet walk kind of a situation. We talked about various use cases where you have, this was the first two use cases were L2 forwarding and the next two were L3 forwarding. And we learned about various options like flooding, spine proxy. We learned in L3, there were things like pervasive gateways, pervasive routes. We learned about the ARP gleaning approach and so on, right? So all of that was happening in your forwarding stuff. Then we went to ARP, especially, because ARP is a very important traffic, and we wanted to understand what really happens for ARP traffic in ACI, right? And we mainly dwell into that over here. We looked at the main meat here is that you need to understand that the ARP has been optimized for ACI to and it has been changed from broadcast to directed unicast, but you can still go back to flooding if you want. But it is always better to use the optimal approach and use the intelligence which ACI brings to the table instead of just flooding ARP like you would do in a traditional network. Then we learned about multicast, right? Two options here again, flooding and optimized approach. We learned how the FTAG trees are created, how they really help with the whole load balancing situation there, instead of congesting your network with a lot of multicast traffic. And finally, we learned policy enforcement, where we understood how once you create contracts, right, how are they getting actually enforced, right? Where are they really getting enforced? So that again depends upon if the leaf knows about the source and destination EPG and the contract associated with it, then the enforcement can happen at the source. Or the leaf, what it does is, if it can't enforce, what it will do is it will send the source EPG information right in the packet, so that the destination leaf can take the final decision on either forwarding the packet or denying it, right? So hope that was useful, and I know this has been a long video probably. I'm not even sure of the total length right now while recording it, but hope it's been useful, and I'm gonna put timestamps, and I'm also gonna put a couple of good readings, right, probably at the bottom, very good readings I'm gonna put links to probably white papers and maybe Cisco live presentations, which would really solidify your your concepts and will really help you with your ACI understanding. Hope that's been useful, and thanks for watching. Bye guys.